Hi, and welcome to the pharmacology of the synapse. In this video, we will explore the different subtypes of brain nicotinic receptors. In the previous video, I mentioned that there were many different subunits that can make up a brain nicotinic receptor. Each of the subunits that have been found in the brain have a unique expression pattern. This figure shows the expression patterns of different nicotinic receptor subunit transcripts in mouse coronal brain slices, as detected by in situ hybridization. So we are looking at mRNA levels in this picture. Some subunits are very widely expressed, such as the beta-2 and the alpha-4 subunit, whereas others, such as alpha-6, beta-3, and beta-4, have restricted expression patterns in the brain, but very heavy expression in those areas. Since there are so many different subunits in the nicotinic receptor family, there can be many different combinations that make up a receptor. However, not every combination is possible. The alpha-5 and the beta-3 subunits are called orphan subunits since they lack a ligand binding site, and thus they cannot form functional receptors without other subunits in the combination, since the ligand binding site is at the interface between the two subunits. So a receptor composed of only alpha-5 and beta-3 subunits is not possible. The combinations that have been discovered can be grouped into two broad categories: heteromeric receptors and homomeric receptors. The heteromeric receptors contain alpha and beta subunits. Homomeric receptors contain only alpha subunits. The alpha-4 beta-2 combination is the most widely expressed heteromeric subtype and is also the most widely studied subtype. The alpha-3 beta-4 subtype is heavily expressed in ganglia. The alpha-5 alpha-4 beta-2 subtype is widely expressed throughout the brain. And some combinations can be quite complex. The alpha-4 alpha-6 beta-2 beta-3 subtype is heavily expressed in the reward regions of the brain. Again, these are just examples of some of the subtypes that have been discovered and is no way a comprehensive list. You'll notice that the subunits listed here do not add up to 5 subunits. For the alpha-4 beta-2 subtype, this receptor can exist in two different stoichiometries. There can be 2 alpha subunits and 3 beta subunits, or 3 alpha subunits and 2 beta subunits. For some of the other subtypes listed in the heteromeric category, such as the alpha-3 beta-4 subtype, the exact composition of the subunits in this subtype may not be clear, but we know that they contain alpha-3 and beta-4 and thus are categorized by these more interesting subunits. For the homomeric receptors, they contain only alpha subunits. The alpha-7 subtype is the most widely expressed homomeric receptor subtype, and the alpha-9 and alpha-10 combination has limited expression and is found in ear cells. This is a cartoon of a sagittal section of rat brain, and this picture illustrates the complex and mixed expression of the different nicotinic receptor subtypes. Some brain regions have only 1 or 2 subtypes, whereas others, like the ventral tegmental area and the substantia nigra, contain a lot of different subtypes. In addition to different expression patterns, each receptor subtype has different receptor properties. There can be differences in ligand binding. Certain agonists and antagonists affect a particular subtype more than others, which we will talk about more in the next video. The rates of desensitization of the receptors can also be different. In the reward areas of the brain, the alpha-4 beta-2 nicotinic receptors desensitize more rapidly than the alpha-7 nicotinic receptors, which will be important in mediating the addictive effects of nicotine when we talk about that in the complex neuromodulation video. Also, calcium permeability can be different. In general, the alpha-7 receptors have higher calcium permeability than the other receptor subtypes. All of these receptor subtype properties were discovered by expressing the receptors in cells in vitro and then testing for different receptor properties. So how do we know what the receptors do in vivo in light of their complex expression patterns in the brain? We will address this question in the next video.